Okay, what does it say?
So you need to get, so this one it says, so it says the limit x equals 0, right?
The limit as x approaches 0?
Yes, and then g of x, then it says where x, so x, and then it's like an inequality, you know what I mean? So it's like, yeah?
Yeah, sort of. X squared is less than or equal to g of x less than or equal to 2x.
Is this it?
Yes, but the other way.
Over and around.
Oh.
So just change the x's. Oh, yeah.
And then 2x squared.
Like that?
Yes.
Is this correct?
Yes. Yes.
Okay. You're asking what is the limit as x approaches 0 of g of x. Okay. And it says that we don't know what g of x is, but this is always true. This young man over here said that it's the sandwich theorem, right? So what should we do if we're going to utilize the sandwich theorem?
You find the limits of the two outside ones.
These guys, so are you suggesting I take the limit as x approaches 0 of the two circled in yellow? Okay, this is the same thing as evaluating the function at 0 plus alpha, right? Which is equal to 2, 0 plus alpha, upon squared, which is the same thing as 2 alpha squared, which renders what real result? 2. Zero, right? Because 2 is being multiplied by an infinitely small number squared. So it's going to render the real result 0. Okay? And I utilize alpha because when we square it, it doesn't matter whether it was negative before. A negative number squared is a positive. Positive number squared is a positive, so it doesn't matter. So now let's do limit as x approaches 0 of x squared. This is the same thing as evaluating the function at 0 plus the alpha. This is the same thing as alpha squared. Again, this is, we can use alpha. We don't have to do case by case. Which is equal to alpha squared, which renders the real result what?
0.
Yes. The left hand and the right hand limits agree. So by the squeeze theorem, this implies that the limit as x approaches 0 of g of x is 0. And this is one of those rare examples where I will let technology be out because your textbook is purely online. But what I would suggest is write the problem down on a piece of paper so you don't have to have your cell phone out. Yeah. Okay. Do you have any other questions?
Well, on 47, so it says, numerically that estimate the limit.
Mm-hmm.
So, and its limit when x approaches 0, and it's square root of 1 minus cosine of x over x.
Everything over?
Yeah, everything over.
Over x? Okay. How are you going to do this?
So what I did was like the normal thing, right? Like the omega, the little omega, and then, whenever it's positive and then it's negative, right? So
It says numerically do it, not algebraically.
So that's what I had the question of.
Right.
How do you do that?
So what's in the yellow is f of x. If we're going to approach 0 from the left, let's say this is where we approach it from the left. And let's say here's when we decide to approach it from the right. We're going to pick values of, let's say, negative 0.001. evaluate the function at that value. See what that outputs approximately. Then at negative 0.01, see what this is approximately when we evaluate our function. And at negative 0.1, see what this is equal to approximately when we evaluate the function. And yeah, at this point, you can use a calculator, right?
Right?
And yes, you can.
Oh, okay.
Yeah. It says numerical, right?
Yeah.
We utilize numerical methods when analytical methods do not exist. So I'm working on it, guys. I'm working on the analytical methods. But until I can solve it, the computer guys win. The computer people win because they can program a code to just calculate these values. Okay? That's a very powerful thing. It's a very good thing. Computers are very awesome. As long as they stay in their lane and not trying to take over humanity. You guys know about the perils of artificial intelligence? Yeah, okay. I'm watching you. Hey, you, I'm watching you. Don't try any funny business. You too there. Also, that's approaching it from the left. Approaching it from the right is when you plug in a positive 0.1, see what the function does. Positive 0.01, see what the function does. Positive 0.001, see what the function does. The function should be approaching a value from the left and from the right when you do this. I'm not going to type it away. That would take too much time. I have to get back to lecture. But you just plug in values. So for here, negative 0.001, plug that in for x and see what you get.
And so let's say the values, like whenever it's positive and then whenever it's negative, they're not the same, right?
Mm-hmm.
So that would mean that the limit doesn't exist. So
that would mean the left-hand limit and the right-hand limit are like two different values.
So should I like in that case, should I write just like that does not exist?
You would say it seems like the left-handed limit is approaching this value, write it explicitly. Then you say the right-hand limit appears to be approaching this value, write it explicitly. Say that by definition, these two values aren't approaching each other, so that means by definition, the total limit does not exist. The left-hand and the right-hand limit possibly do exist, but the total limit does not. No problem. My pleasure. Any other questions before I move on? Okay. So where did we leave off here? We're on 1.6, right? We started 1.7. Oh, okay. Oh, that's right. That is right. Started 1.7.
I think we're on rational.
Okay. The continuity of rational. Let me see here. 1.7. Oh, yeah, that's the way I've organized this. 1.8. I need to put this over here so I can see the page numbers. Here we are, 1.7. And then linear functions are continuous. We proved that. We proved rational functions are continuous, right? I recall we proved that. Okay. Then we're going to talk about, so it implies that if linear functions are continuous, rational functions are continuous, it can be shown that radical functions, trigonometric functions, they're all continuous.
Yeah, so we are on 1.7 already?
Yes.
Okay.
So linear, rational, radical, ECT, oh, trig are all continuous. And we'll show this slowly. Okay? But they're continuous on their specific interval of being defined, right? For example, this function 1 over x, is this function continuous? It is.
No, not at zero.
Not at 0. But what if we said the domain of this function, let's restrict the domain to this. Then it is continuous on this domain. Yeah. So 1 over x can be continuous. You just have to give it the appropriate domain, meaning the appropriate set of numbers that we can plug into it with nothing messing up. Notice that the only thing that can mess up here is division by 0. What about this? Is this function continuous? This is a function. This is a rational function right here. This was a rational function. This is a radical function. Is this function continuous?
Well, not if it's like less than 0.
What less than 0?
The x. The x is like the domain one. If the domain is less than 0, then it's not,
You mean x minus 1 has to be greater than or equal to 0, right?
Yeah.
So then when you solve, you get x has to be greater than or equal to positive 1. So its domain is what? Including the 1, right? Because x can actually equal it. So from inclusive 1 to positive infinity, it's a continuous function, but not for all reals. Okay, what about this function? Is this function continuous?
No. Yeah. Yeah.
For what domain?
Oh, I think.
All reals?
Yeah.
Yeah, there's nothing you could input into cosine that it won't output something. Okay. So you guys get it. So now let's do like a combination of them. Like, what is f of x? Square root of x plus 1 all over x plus 1. Where is this function continuous? Well, there's two things that can go wrong, right? Division by 0 and square root of a negative number. So to prevent division by 0, we say that this cannot happen. The denominator cannot equal 0. This implies that x cannot equal negative 1. Then we say that what's inside that radical has to be greater than or equal to 0, so that it prevents it from ever being negative. And this implies that x has to be greater than or equal to negative 1. So notice that this says x can never equal negative 1. And this says x can be greater than or equal to negative 1. We have to remove this. We have to remove this, even though it is true, it was logically possible. This is telling us, oh, given the denominator being this, even though the numerator has this possibility, we have to restrict it to adhere to what this piece of information is saying. So what it's saying is we can't be 1, we can't be negative 1, and we have to be greater than negative 1. So on the number line, here's 0, here's negative 1. Basically, we're everything except negative 1 to the right. So the domain in which this function is continuous or defined is from not including negative 1 to positive infinity. Okay. So that's how those problems work. So even polynomial, rational, radical, trigonometric, we can find an interval in which they are continuous. Okay. So notice that if f is a function that maps the reals to the reals, and f of x is continuous, we can say this: the limit as x approaches k of f of x is just f of k. Recall that that secretly means f of k plus alpha is the same thing as f of k. So we get this whenever a function is continuous, meaning whenever we're approaching the limit as, if the function is known to be continuous, well, we could just evaluate the function at that k, and it'll output what the limit is, because it's a continuous function. The left hand and the right hand limits should agree, because there's no jumps. So then let's evaluate the limit as x approaches to the square root of x cubed minus x squared plus x all over x squared. That would be a tough one to do if you didn't know that this was continuous, right? Actually, I'm going to remove this square root thing. Okay. And you know what? I'm going to remove this x squared down here. All right. Let's just do this problem. We know this is a polynomial equation, right? So that means that we can evaluate f of 2 to know what the limit as x approaches 2 is. So we don't have to do the plus omega, we don't have to do the plus alpha. We know that x cubed minus x squared plus x is a continuous function. So we could just evaluate it. Same thing. What about the limit as x approaches pi over 2 of cosine of x, sine of x, tangent of x? They're all continuous because they're trigonometric functions, and we'll prove that later on. So we can just plug it in. It becomes cosine of pi over 2, sine of pi over 2, and I'm going to avoid, actually, don't have to avoid tangent. Oh, yes, I do. I'm going to switch this to cotangent. Let's switch this to cotangent. Okay. Here's why I switched it to cotangent. If it was tangent of pi over 2 is sine of pi over 2 over cosine of pi over 2. But notice that that's 1 over 0. We're dividing by 0. That's not in the allowable domain of that function. But cotangent works because cotangent of pi over 2 is cosine of pi over 2, sine of pi over 2. What this is 0 over 1, and 0 over 1 is okay. 0 over 1 is 0. So this reduces to a 0. This reduces to a 1. This reduces to a 0. So our overall limit evaluates to a 0. Okay, so just know that if you know that your function is continuous and you want to know what the limit is, just plug that value into the limit. plug the value of the limit into the function. This process is called direct substitution. You directly substitute the value of the limit that you're approaching into the function. What about this one? Is this function here continuous? This function is not continuous?
Not at, -1.
Ah, so it is continuous from this interval. On this domain, is it continuous? Okay. It's continuous on that domain. So that means if I approach the limit as x approaches 0, we should be fine, right? So we'll just replace every x with a 0. Because the sign of 0 is 0. So then we just get the cosine of 0, because 3 times 0 is 0. And the cosine of 0 is 1. So then this becomes -7 times a 1 all over a 1, which is from -7. Okay? So be prepared to be given a function as complicated as this looks and be able to determine what the limit is. You don't want to try and evaluate this limit algebraically, with 0 plus omega, 0 minus omega. That would take a long time. You want to recognize that it's a continuous function, and where does the domain in which which is defined, that means that domain of inputs causes it to be a continuous function. Then you can just evaluate to find the limit. Okay. So moving on here, let's talk about the intermediate value theorem. Okay. So let's say you have a function. Here's x, here's y, here's a, here's b. The function does something like this. Or this is your f of a. And this is your f of b. Okay. The intermediate value function says that between a closed interval, AB, that in a closed interval AB, there exists some element C inside this interval AB, let's say right here, such that f of C, such that f of C is between f of A and f of B. Now, there's some conditions that need to hold here. The function f of x has to be continuous. And it has to be defined on this closed interval. Then we can say that this is true. Why is continuity necessary? Well, because we can construct a very similar situation. Call this A, call this B, have a function like so. And actually, let's put just a hole here. That's not how to define that, for example. Okay. Notice that we can't say the statement of the intermediate value theorem anymore. So continuity is required. So here's the formal definition, and this is why the continuity is necessary. Now that we've got the picture, here's the formal definition. Given a function f that maps the reals to the reals, such that f is defined on some AB, such that f maps AB onto the reals, and f is continuous. That implies there exists some C in A and B, the interval, such that f of x is equal to f of c for some x in this. And for instead of for some, we can say for at least one. Even though for some is true. Saying for at least one is a little bit more revealing. The reason we say for at least one is because we have this situation like so, where it crosses the line once. But we have another situation where we can have a continuous function, but it could be doing something like this, and it would cross it multiple times. So we say for at least once, for at least one, that it will touch it. So the intermediate value theorem is basically saying, if you have a function that starts down here, and it's continuous, and it travels up here, that it must have crossed the x-axis. That somehow it crossed the x-axis at some point. That's all it says. And this is exactly why this theorem, which we won't prove this theorem, is beyond the scope of this class, unfortunately. I wish we could prove this theorem, but it goes to show that the intermediate value theorem, once it's been proven, can reveal that you have known roots for your function. A root for your function is a value such that when you plug that into your function, it outputs a 0. So the intermediate value theorem will be able to determine where it will be able to prove the existence of roots given the continuous function. All this stuff seems like, obvious, right? Well, duh, of course, it has to cross the x-axis. Why are we going to even make a big deal out of it? Well, something so simple is actually very difficult to prove in a rigorous way, in a way in which is like logically sound, airtight, no possibilities for any kind of logical inconsistency. It is actually difficult. Can be done, but it's difficult. So that's why it's kind of a big deal. So for example, let's take a function. All right. What does this function look like when we graph it? Well, it's a parabola. And it's vertically shifted by 1 vertically down. So this is your f of x equal to your x squared minus 1. The intermediate value theorem says that, we can assert that this function has roots, in this case 2 roots, because for some values, let's say f of 0, it assumes a negative value, and for other values, let's say f of plus or minus 2, for values of plus or minus 2, it becomes plus or minus 2 squared, which is 4. So if it used to be at a negative point, and now it's in a positive point, it must have crossed the x-axis. So that's one way to prove that the roots exist. Another way to prove that the roots exist is to find them algebraically. Set it equal to 0. When you take the square root of both sides. That's why it's touching here at -1 and +1. But there's some functions in which algebraically solving for its roots are not possible yet. That is why the intermediate value theorem is important, and the approximation methods and the numerical approximation methods are important. Okay. So for example, let's say our function is . And we want to know, okay, does it equal 0 ever? Between x is equal to 0 and x is equal to 1. Does it ever equal 0? Well, let's evaluate the function at f of 0. Sine of 0 is 0, so this ends up equaling a negative 1. One minus 1 is 0. Sine of 1 is approximately like 0.8. Or is it? Yeah, 0.8425. So notice at f of 0 is a negative value, and at f of 1 it becomes a positive value on the y-axis. That means, here's our function, f of 0, it's at negative 1. All right, and at f of 1, it ends up being almost 1. Because f of x is equal to x squared minus 1 plus sine of x is a combination of polynomials and trigonometric functions. It is a continuous function. That means somehow it has to have continuously, by some path that we don't know yet, it must have continuously connected those two dots. And that means by the intermediate value theorem, somehow there is some point here that it crossed the x-axis. And that is the root. That is the solution to this equation. That is the solution to this equation. So this right here, showing that it was negative and then it turned positive, by the intermediate value theorem, we can say that that implies that there exists a root. That there is a solution to that equation between x is equal to 0 and x is equal to 1. But what is the value of the solution? If we know it exists, now we want to know what it is, right? Okay. So how do we find it? Well, what you do is, now you try and evaluate the function at some intermediate point. Okay, what about f of 1/2? Well, then that's just 1/2 minus 1 plus sine of 1/2. Okay. I'm actually going to change it from 1/2 because I don't know how to evaluate sine at 1/2. Why don't I pick f of pi over 6, for example? Because I do know pi over 6, I can evaluate sine at pi over 6. And the numerical value for pi over 6, let's calculate it, is 0.52. So, and you know, that's basically like 1/2, except now we can evaluate sine. So this becomes pi squared over 36 minus 1 plus, what's the sine of pi over 6? My student who took trig with me, what's the sine of pi over 6? What's that? That's right, it's 1/2. All right, so this is approximately, whenever you do all of the computations, let's see, it's a pi squared divided by 36 minus 1 plus a half. This is approximately negative 0.22. So we're close. We're close to that 0 because we're getting really close to 0. That's a number close to 0. And it's much closer to 0 than this is. Okay? So then you think, okay, if this is approximately 0.52 and that outputs that, what is another good guess to put in? So this method is called the bisection method. So you got a 0 and you got a 1. So we picked and we knew this was negative, this was positive, so we picked some value approximately halfway between them. We found that some value halfway between them outputs something negative. So here to here, it's negative. Here, this was negative, this was negative. So let's pick something in between here, because that is going to give us something even closer to 0. All right. Going to this side will only get us closer. Oh, did I mix it up? You know, I didn't mix it up. Going to this side, f of 1 is what gave me positive. F of 0 is what gave me negative. Going to this side is only getting me closer to negative 1. Going to this side is going to get me closer to 0.8425. And we're already at negative 0.22 here. So let's scoot over just a little bit in between them. What's in between 1/2 and 1? I mean, yeah, you could say it's 1/2 plus 1 and half, which is 1 plus 2 all over 2 all over 2, which is 3 over 2 all over 2. Multiplied by reciprocals, you get is 3 over 4. All right? So what about f of 0.75? Well, when you plug that in, you get approximately, let's see what you get. 0.75 square this minus a 1 plus a sine of it we get negative 0.42. So it seems as if that got us a little bit farther away from what we wanted. This was a little closer, right? So what are you going to do? So on what side? On the left? On the right? Notice if you're on the left, all the way here, the function at 0 evaluated. The function at 0 evaluated a negative 1. The function at 1 evaluated 0.8425. Here in the middle, we got a really close value, negative 0.22. We picked something between those, and we got this, which is actually taking us farther away.
So does that mean that the graph is going like this?
Well, it means that the graph is connecting, as I erased, but it means it's connecting the points negative 1 and 0.8425. Here's negative 1. Here's 1. Here's 1. And it's connecting these 2 points somehow. We don't know where. But at some point, it crosses the x-axis. And that's what we want to find, right? Okay. So we could try putting in 0.6. And we find that 0.6, f of 0.6, This ends up being approximately negative 0.075. Very close, right? When we went halfway between these guys, it was too far. So we scoot a little bit back, right? And then you see that, oh, that's almost zero. To one decimal place, it is zero. To 2 decimal places, it's not. So then you could pick another point. It just so happens that if you do this process, you find that f of 0.64 becomes approximately this. And to 2 decimal places of accuracy, that is 0. So it depends on how accurate you want your value. So if you want it to 2 decimal places, you're done. This, if I chop it off from here, it is 0. If I throw those the digits past to the right of the yellow line, it is 0 for all intents and purposes. But it's not fully 0.
So does that mean that it crosses the x-axis 2 times?
No, it just means it crosses the x-axis near 0.64. So here's 0.5. It's going to cross the x-axis for the input near 0.64. That's where the function is going to cross the x-axis. F of 0.64 is nearly 0.
Just like, hold up, before you move on,
Mm-hmm.
I'm just a little bit confused. Because whenever it's 0.6, it's negative 0.075, right? And then whenever it's 0.64, it's positive 0.0068. You know what I mean? So that means that it needed to like cross and then come back down.
It didn't cross and come back down.
So how does it like if you like let's say we're
this is a number to the left of this number. It was negative here, but now it's positive here. So it's not jumping back and down. It's just moving. It's just moving.
Oh, okay, yeah, that one. Yeah, okay. No, yeah, you're right on that. But like on the 0.75, that one goes back down because it's negative 0.42.
Yeah, wouldn't it cross in 2 places at x if it goes up at 0.64?
It very well could.
It goes back down to a negative.
It very well could.
And then it goes back up whenever it goes to 1. Right?
Yeah, it very well could. Yeah. Actually, if you find 2 points of the function, let's say I find some point f of a, which is less than 0. Then I find some f of b, which is greater than 0. That means it crossed the x-axis. Any 2 pairs of points, that means it crossed the x-axis. And yes, this function can do it multiple times. And here's why. That sine is a trigonometric function and it oscillates. So of course it's going to cross the x-axis for multiple points. Yeah. It's a good question. Very good question. So the question was find a solution to approximately 2 digits. You can find any solution. I wouldn't ask you to find all solutions, but maybe I would. So keep that in mind. I find these problems a little, when I'm having to calculate a whole bunch of things, as useful as it is, I lose interest. If I'm like typing stuff into a calculator, I lose interest. It's very important though. It has a lot of practical real life applications. So it is not that bad. Okay? It's
So
not that bad.
That answer would be the 0.64, right?
Yeah, to like 2 places of accuracy. That is a solution. But it's not the solution.
Because there's like a lot of them, right?
There can be a lot of them, yes.
Because you're trying to get to 0, right? Like
yes.
You're trying to approximate over there, so that's why there
yes.
can be like a bunch of them, right?
Yes. Yes. Yeah, that's right. That's right.
A little confusing, but.
It's okay. With practice, it'll get better. Let's see here. Okay. So, yeah. Let's see here. So next class period, if we meet on Wednesday, I don't know what's going on. I'm really loving this cold Arctic weather. If we don't meet on Wednesday, I'll probably be in Lake Hefner swimming in the icebergs. So I hope so. I want snow. I want cold days.
Me too.
Let's go outside and swim in the frozen lakes.
What?
Yeah.
You know, it's just like, no, it's fun. Like the first 5 minutes, after that, you get tired of it.
Yeah, we'll see.
Why? What's going on? What's happening?
So there's gonna be a lot of cold weather.
This week?
Yeah, for like a whole 9 days. Yeah.
We're gonna reach 0 at one point.
Yeah.
That's it.
We're gonna get a wind chill of -10 degrees wind chill on Saturday and Friday.
I don't think we get below 0. I know they did say on one day we're supposed to reach 0.
Yeah. Yeah.
I don't like that.
I do. I do.
I don't like that at all.
Many people don't like the
It's
cold.
gonna hurt.
Yeah. So I don't know when we're gonna meet again, but when we meet again, I will prove why continuous functions, why the polynomials, we already proved that. Why quadratics are continuous, why trig functions are continuous, why combinations of continuous functions are continuous, why addition of continuous and subtraction of continuous is continuous, why the multiplication of continuous is continuous, why the division of continuous is continuous, why multiplying a continuous function by a constant is also continuous. Also, the composition of two continuous functions is a continuous function. Did I say continuous enough?
Continuously.
Continuously saying continuous? Okay, that's what we'll show, and that will be the second half of 1.7. Then we'll be moving on to 1.8, and that's the final section before the exam. Your exam is probably won't have to happen, not this week, but next week on your lab period on Thursday. So that's that.